In this video, we will be looking at how two planes can intersect. So first of all, if they actually intersect, there is no point of intersection. We actually have a line of intersection. Then the other two scenarios come from if the planes are parallel to each other. They can be parallel and distinct and have 0 points of intersection, or they can be coincident planes, meaning the planes are the exact same, they're on top of each other, and then we have an infinite number of solutions. Any point on one of the planes is a point of intersection with the other. So the first thing we're going to do to solve is to see what scenario we're in by checking the normals. If you can multiply one of the normals by a scalar to get the other one, it means that your planes are parallel, which means you're in one of these scenarios. And we can differentiate between these two by checking that constant at the end to see if our planes are parallel and distinct or coincident. If the normals are not related to each other whatsoever, we have a line of intersection, and then we're going to use elimination or substitution to solve for that line of intersection. So let's give it a try. Determine the intersection, if any, between the two planes. So first thing, I'm going to write out my normals. -2, 3, 1 for the first. 3, -1, 2 for the second. They're not scalar multiples. So the planes are not parallel. So that means we will have a line of intersection. So I'm going to look at my two plane equations, and I think I'm just going to eliminate the y's. That seems pretty nice. So I'm going to take plane 1 and I'm going to add triple plane 2. That way the y coefficient would be -3. So we have -2x plus 3y plus z plus 6 equals 0. And then tripling the second one, 9x minus 3y plus 6z minus 6 equals 0. And because the y coefficients are opposite signs, I'm adding my lines here. So that's 7x, the y's are gone, plus 7z plus 0 equals 0. Now, I chose to eliminate the y's. You could have eliminated any of the variables, that's fine. Depending on which variable you eliminate, your vector equation of the line might be different, but it could still represent the exact same line of intersection. So from here, because we know we have a line of intersection and the vector equation of a line has that parameter in it, I'm going to set one of the variables that I have left equal to the parameter. So I'm just going to say let x equal t. And that is actually our first parametric equation. And now I can sub that in to that 7x, but instead I'm going to put 7t plus 7z equals 0. And then I'll isolate for z to get my next parametric equation. Then divide by 7. So there's another parametric equation. And now I'll sub both of these into either the plane 1 or plane 2 equation. I'm going to go into the second plane equation. So I'll have 3, but instead of x, I put t, minus y, and then plus 2z, but z is -t. So I'm just going to write minus 2t, minus 2 equals 0. I'm going to bring the y over to the right. And that way the coefficient is positive right away. And now I'm just going to collect my like terms. So t minus 2 equals y. And there's my final parametric equation. Now I'm ready to go to write my vector equation. Now, just for ease of writing the vector equation, you can also write your 3 parametric equations nicely lined up, write your constants in the same place. So x, I can write it as 0 plus 1t. Y is -2 plus 1t, z is 0 minus 1t. And if you do that, there's your r naught vector, and there's your direction vector. So therefore, the line intersection is 0, -2, 0 plus t times 1, 1, -1, where t is an element of all real numbers. All right, next one. Let's check those normals. So the first normal is 1, -2, 3. The second is -3, 6, -9. And I can see here that if I multiply the first normal by -3, all the components, I do get n2. So therefore, we know they're parallel. But we want to see, are they parallel and distinct, or are they coincident? So if I can use this exact same scalar on the constants, then they're coincident as well. So let's see, -3 times 1 gives me -3, which is the constant for plane 2. So that means, therefore, the planes are coincident. This means infinite solutions. Any point on the plane is a point of intersection. Now, let's say you didn't check the normals to begin with and you went straight to your elimination. Let's see what that would look like. Well, let's say I wanted to eliminate the x's, and I said I'm going to multiply plane 1 by 3, and then I would add it to plane 2. Okay, so that would be 3x minus 6y plus 9z plus 3 equals 0. Plane 2 is -3x plus 6y minus 9z minus 3 equals 0. And then I would add my planes. And then I would end up with everything canceling out, and I would get 0 equals 0. The variables are all gone, but I have this true statement which would tell me there's an infinite number of solutions. And in this scenario, infinite means that the planes are on top of each other, and therefore any point on one of the planes is a point of intersection with the other. All right, let's look at the next one. Checking the normals first. 1, -1, -2, -4, 4, 8. And it looks like if I multiply the first normal by -4, I'll get the second. So I know they're parallel. Now let's see if that same connection applies to the constant. -4 times 1 is -4, not -3. Therefore, the planes are parallel and distinct. No intersection, no solution. Now, if I were to try to do elimination here, my variables would cancel out, but then I'd have a false statement. So that would be my clue that there's no intersection. All right, next example. Do the following planes intersect? If they do, what is the intersection? So, checking the normals first, of course. 1, -1, 1. 2, 2, -2. Although it looks like I could double my first normal to get the second, the negative placement messes it up, because 1 times 2 is 2, -1 times 2 is -2, so not parallel. So I'll start trying to solve. So I'm going to double the first plane, and then I'll decide what I want to eliminate. All right, so now I have some options here. I can eliminate x and then be left with y and z, or I can eliminate both y and z at the same time, because adding the lines would eliminate them, and then have x right away. Now remember, we do have a line of intersection, so I will need a parameter at some point, but either way is fine. I'm actually just going to eliminate both y and z, just to see what would happen. So I have 4x That's 0 equals 9. So x equals 9 over 4. That's your first parametric equation. And actually, that would be 9 over 4 plus, let's say, 0t. Okay? Now, because I know I need a parameter, I actually don't have to go in and eliminate again. I can just say, well, if I know x is 9 over 4, I can let y or z equal to t, let's say, and then isolate for the other. So I'm going to say y. Y is just t. And I'll write it as 0 plus 1t for later on. So I'll sub that into plane 1. So instead of x, I'll put 9 over 4. Instead of y, I'll put t plus z equals 3. And then I'm going to bring everything over. So when I bring the 9 over 4 over, I'll have 3 minus 9 over 4. And 3 is 12 over 4. So 12 over 4 minus 9 over 4 is 3/4. And then bring the t over and it's now positive. And there we are. So therefore, the line of intersection is, so our vector r0, 9 over 4, 0, and 3/4, plus t times 0, 1, 1, where t is an element of all real numbers. All right. Now, a little note. When you have planes that will intersect at a line, there is a nice little trick that we can use to check our work. Now, whatever the line of intersection is, this line exists on both planes, which means the normal of plane 2 will also be perpendicular to the line of intersection. And the normal of plane 1 will also be perpendicular to that line of intersection. Which means if you take the cross product of your normal vectors, you're going to get a vector that is perpendicular to both normals. And that vector will actually be collinear to the direction vector of your line, because the line is perpendicular to both normals. So let's use this idea to check our answer from the previous question. Now, in the previous questions, our first normal was 1, negative 1, 1, and our second normal was 2, 2, negative 2. Let's take this cross product. So I'm going to put negative 1, 1, 1, negative 1, 2, negative 2, 2, 2. Okay, so that's 2 minus 2 is 0. 2 minus negative 2 is 4. 2 minus negative 2 again is 4. Now, the direction vector we got from our previous line, so I'll put M for direction vector, was 0, 1, 1. And look at that. Those are collinear vectors, which is exactly what that test told us we would get. So I can write my direction vector as a quarter of that perpendicular vector I just got. So that's great. Finally, find the parametric equation of the line passing through this point that is parallel to the line of intersection of the planes. Now, the long way to do this would be to find the line of intersection. But if we want to be parallel to that line of intersection, we just need a vector that is collinear to the direction of our line. And what did we just find? That if we take the cross product between our normals, we will get a collinear vector. So let's give that a try. And this is just to speed it up, which we always want to be more efficient if we can. So, negative 5, 7, 3, negative 5, 3, 2, 4, 3. And now we have negative 10 minus 21. We have 28 minus 6. and we have 9 minus negative 20. So now if we want our line to be parallel to the line of intersection, we just have to be collinear to this, which means we can use exactly that vector. And if we have to pass through this point, then that could be our vector r0. And here we are. And this is a lot more efficient than actually finding the full line of intersection. So there's our vector equation, and for our parametric equation, 1 minus 31t, negative 7 plus 22t, and 5 plus 29t. And that's it for the intersection of two planes.